Good morning, Amherst. May is approaching. May is turkey season, so I'm looking forward to the bright sunrises. Go out and pursue me the great North American wild turkey. That's the hen call. Anyway, I'll keep you informed as to how that goes. Friday, turkey season opens, so if you see a feather on here, you know what happened. All right, going to talk about titration today. We were doing a little bit of nomenclature yesterday, and we did our acids and bases, and we did neutralization equations, and I posted the key. But let's talk about this in the real world. If you have a solution of unknown concentration, you want to figure out, well, how strong is that? Is that a fairly concentrated solution or a weak solution? What is it? You add the opposite until you reach a neutral solution. And then you add an extra drop to make it not neutral, so you can tell in the presence of an indicator, table M, what's going on. So basically, you take a burette and you take your solution of unknown concentration and you fill it up. There's technique to that. I have some videos of it attached. Wish we were doing lab, we're not. So anyway, you take a burette, you fill it up with a solution that you're trying to figure out how strong it is. You have a previously measured volume of a solution that you know the concentration, and you add a little bit of indicator to it. So you put an Erlenmeyer flask in, and you can use another burette, or you can use a graduated cylinder, whatever you want to use, but you know the volume here, and you know the concentration, and you put in a little indicator. And what you're going to do is you're going to add the unknown solution to the known solution until they're neutral, and then one more drop makes the indicator change color, and you can backtrack and figure out the concentration of the unknown. So basically, good morning, tungsten. So you record the initial volume on your burette, and you dispense, and then you record the final volume, and the difference in volume there is going to represent the volume of the solution that you dispensed. And that's how much volume you needed to exactly neutralize the volume that you had in here. So when the moles of the hydrogen ions from the acid equal the moles of the hydroxide ions from the base, the solution becomes exactly neutral. It's pH 7. We'll talk more about pH later. So if you add even a half a drop of an additional acid or base, you're going to make that indicator change color. So indicators, there are thousands of them. Tungsten. Yeah, he wants to go pursue turkeys too. So they give you 1, 2, 3, 4, 5, 6 indicators here, but there are thousands of them. Phenolphthalein, interesting spelling, phenolphthalein is most commonly used for acid-base titration, and below pH 8, phenolphthalein is colorless, and above pH 9, phenolphthalein turns pink. Somewhere in between 8 and 9, it turns pink. Well, to go from pH 7 to pH 8, even one drop of additional base added to an acid is enough to take that phenolphthalein and go into the color change area range, and it's not a significant volume change, not something you can measure to any degree of accuracy on a burette. So it's enough to make the color change. You know that you've added enough base to the acid. So here's how this works. We'll go over an example. Let's say I have a volume of base in my burette, and it's filled up, and my initial volume is 1.07 milliliters. You read it from the top down to the bottom of the meniscus, and 1/10 of the smallest division, and you measured it previously, and it's 0.106 molar sodium hydroxide. So in your flask, you take a graduated cylinder, you add it doesn't matter what the volume is, let's just, I'm making these numbers up, 15.2 milliliters of hydrochloric acid, and you don't know its concentration. You add a couple drops of phenolphthalein. It's a C table M. We just talked about table M. So you slowly dispense sodium hydroxide into the acid until less than one drop of the base into the acid makes the solution turn pink, faint pink, for 15 seconds or more. That's what they call the end point of this titration. So Let's just say you dispensed, and your final volume here was 13.7 milliliters, and you get a light pink solution, and that stays for 15 seconds or more. Usually do these in 2s, 3s, 4s. The more you do it, it's more accurate, larger range of data. So let's summarize. You've got some acid, you've got some base. You don't know the concentration of your acid, that's what you're trying to figure out. You know the base is 0.106 molar. You know the initial volume of the acid, you know the final volume of the acid, you subtract off, you know the volume of the acid you dispensed. You previously measured the volume of the base you dispensed. Now if you go to table T, they've got a titration equation here. I don't really appreciate the way they did this. They said MAVA equals MBVB. There are lots of ways to do this. I'm okay with the algebraic solution the way they do this, but I don't really care for the fact they just called MA the molarity of the hydrogen ion and MB the molarity of the hydroxide ion. It's not taking into account how many hydrogens and how many hydroxides are in the formula of that acid or base. So I want you to add X and Y to that equation right here. I want you to put X here and a Y there. And here's what this all stands for, okay? So you're going to add those to your thing. X is the subscript of the hydrogen in the formula of the acid. So HCl, in our case, X is 1. There's really a 1 here. If it was H2SO4, X would be 2. If it was H3PO4, X would be 3. You get the point. It's the subscript on the acid, on the hydrogen in the acid. MA is the molarity of the acid solution, and that's what we're trying to figure out. VA is the volume of the acid. In our case, we subtracted off and we found out it was 12.64 milliliters. MB is the molarity of the base, and we said, well, we knew that was 0.106 molar. VB is the volume of the base. We pre-measured it at 15.2 milliliters, and that's got fewer sig figs because we would have used a graduated cylinder in lab. You can use another burette. That's a whole other way of doing it, more accuracy, that's fine. Y is the subscript on the hydroxide ion in the formula of the base. So in our case, NaOH, Y is 1, but if we had used something like barium hydroxide, Y would be 2. You get the point. X and Y do not affect sig figs. They're not measured values. Okay, they are part of a formula. They're by definition, if you will, so you're not going to be down to 1 sig fig based on that. Looking at our data, that's 4 sig figs, that's 3 sig figs, that's 3 sig figs. Our answer is going to have 3 sig figs. Tungsten is very needy today. So here's X MAVA equals MBVBY. Your volumes should be apples to apples. You can't have milliliters on one side and liters on the other side, but as long as they're the same, it's going to work out. If you multiply molarity times volume, molarity is moles per liter, volume, say for example liters, well, you'd be moles. Well, you could also have multiply, molarity, moles per 1,000 milliliters, that's the same, times milliliters, you're still going to get to moles. So when you're done, you have moles of hydrogen ion equaling moles of hydroxide ion. That's when you know you're neutral. Okay, so here's our formula, here's our data. X was 1, MA is what we're looking for. We had 12.64 for the volume of the acid. We have 0.106 for the molarity of the base. We have 15.2 for the volume of the base, and Y was 1. Divide out. This was in milliliters, your answer's in milliliters. Over here, I'm sorry, this is molarity, this is going to be molarity. This is 0.127-ish. All right, not too hard, straight up algebra. Neutralization, just very briefly. If you look at table I, very bottom of table I, you have H positive ions and hydroxide ions, and you're going to form water. That's what you're doing in a neutralization equation. So really quick, let's move to tonight's homework, which is going to be worksheet 3, acid-base neutralization equations. We're going to do front and back. There's multiple choice in the back, and there's some math. Let's do number 6. I'll zoom in a little bit because this is not much room to write. All right. So it says, what volume of 2.0 molar phosphoric acid is required to neutralize 150 milliliters of 1.50 molar magnesium hydroxide? All right, so here's your acid, here's your base. 2.0 molar, that's the molarity of the acid. X is 3, H3PO4. 150 milliliters, that's the volume of the base. 1.50 molar, that's the molarity of the base. Y is 2, because there's 2 here, right? And it says what volume. We're looking for the volume of the acid. Plug and chug. X is 3, MA is 2, VA is what we're looking for, MB 1.5, VB 150, Y is 2. Divide out, take it down to 3 sig figs. You get about 113 milliliters of the acid you're going to need to neutralize that much base. So you've got 6 more on this page, not enough room to write. Apologize for that. That's all right. And then you've got 10 questions in the back, multiple choice. All right, that's your homework for tonight. I'll attach a few videos that show indicators and titration technique because I'm working, with pen and paper here in my dining room table with my rather boisterous cat. All right, have a good one. Look for the key tomorrow.